So today we're going to basically start wrapping up some of what we've been learning here in Chapter 10, and what is, of course, the objective of all of these things. Basically, the reason that we've been covering all this material, these new methods of factoring, is to solve more complicated quadratic equations. You'll recall back in Chapter 6, we learned about quadratic equation. We learned three methods of solving, factoring, completing the square, and, of course, the quadratic formula. So we're going to start tying everything we've looked at together a little bit here and solving some quadratic equations. Now here is my general recommendation to an approach whenever we're dealing with quadratic equations. First is that we attempt to factor it if we can. Factoring is probably the easiest method of solving a quadratic equation, and it works, especially if you practice with it. You'll start to get the hang of it pretty quick and get an idea of what can and cannot be factored. Today we're going to learn something here that helps us to really understand when something can be factored and when it can't be. Let's take a look at this example. For instance, let's say that I am given an example like this of 2x squared minus x minus 3 is equal to 0. So this is my quadratic equation right here. Now I could, of course, proceed directly to the quadratic formula if I want, but these are pretty small numbers here and they look like something I could factor. So let me go ahead and open two sets of parentheses right here. Since I have a 2x, I need two first terms that would multiply together to give me 2x squared. The x squared means that I have an x in each location right here. And 2 times what can give me 2? The only answer to that is to put a 2 here and a 1 here. I don't even need to write the 1, it's just understood. 2 times 1 is definitely going to give me 2. So now basically I need two numbers that will multiply together to give me a negative 3. So I'm going to have to be a little bit careful about where I place the positive and the negative, and where I place the 3 and the 1. Obviously, the two numbers that multiply together to give me 3 are going to be 3 and 1. But I need the result to add together to give me this coefficient right here, a negative 1. So what would happen if I put the 3 right here, for instance? Then I would have 2 times 3 would be 6, and then I would have a 1 here. 1 times 1 is still 1. Is there any way I can combine 6 and 1 and get a negative 1 here? No, there's really not. If, on the other hand, I put the 3 here and the 1 here, then I would have 3 times 1 and 2 times 1. The difference between those is indeed 1. So it seems like I'm onto something by putting the 3 here and a 1 here. Now the question of which one will be positive and which will be negative. The bigger this number right here is negative, that means I need to put a negative sign in front of the bigger term right there. So let's double check and make sure my factoring is correct. 2x times x is indeed 2x squared. Positive 2x times positive 1 is a positive 2x. Minus 3 times x is a negative 3x, so that positive 2x minus 3x is indeed negative x. And lastly, negative 3 times positive 1 is indeed negative 3. So my factorization here looks good. I have two factors, so I'm multiplying this times this and getting 0. So today one of the things we are going to look at is called the multiplicative property of 0, and also the converse of that property. So basically if I have two numbers, any two numbers, let's say I have a number a and a number b, and I multiply them together and the result is 0. Whenever you're multiplying two things and the result is 0, well, there's only one possible way that can happen. One of these things, or perhaps both of them, must be 0. I know either a is equal to 0 or b is equal to 0. That's the only way to multiply two things together and get 0. Either a is equal to 0 or b is equal to 0. So that's exactly the situation I have here. Let's call this 2x minus 3a and x plus 1b. So I'm multiplying this times this and getting 0. So that means either 2x minus 3 is equal to 0, or x plus 1 is equal to 0. So now we have a very simple first order equation that we learned how to solve earlier in the year. So what x value would it take to make 2x minus 3 0? I'm going to, of course, add 3 to both sides of my equation here. Then those will cancel, and I have 2x is equal to 3. Then I'll divide by 2 here, and I have x is equal to 3 over 2. If you prefer, you can call that 1.5, same difference. Here, of course, all I need to do is subtract 1 from both sides. Those will cancel, and I get x is equal to negative 1. So my two solutions for this, x could be either negative 1 or it can be positive 3/2. And this is going to be my solution set right here for this original quadratic equation. Remember, when I'm asking an equation right here, I'm basically asking what unknown value, what x value would it take to make this statement true? This is an equation, not an expression, because it has an equal sign. So what unknown x value would it take to make this the same thing as 0? The answer is, well, there's more than one answer to that. There are specifically 2 answers because this right here is a 2. The 2 possibilities are negative 1 and positive 3/2. Let's double check our answer here. What if I went with the first one of negative 1 and I plugged that in for my x here? What is negative 1 squared? That is, of course, positive 1. Positive 1 times 2 is 2. Negative 1 times a negative is a positive 1, so I have 2 plus that 1, which is a 3. And 3 minus this 3 is indeed 0. So my answer is correct. So we were able to basically solve this one just by observing the factorization of it. Let's try to look at a slightly more complicated example here. Let's take a look at one here where we would definitely have a little more trouble factoring it. Let's take a look at 2x squared plus 15x plus 18 is equal to 0. Now I could try to factor this out just by observation, but that seems like it might be a little bit more difficult here than in my previous example. I could, of course, get better and better at that with practice. But let's take a look at something. Since these numbers are a little more complicated to work with, it kind of begs the question, well, how do I know that this even can be factored? How do I know I'm not wasting my time here by even trying to factor it? Do you remember how in the last section we learned about splitting the middle term? We basically said to ourselves, okay, take a look at this number times this number, and break down the factors of that and see if there's any way we can combine to get the middle term. We call that splitting the middle term. There's a way we can carry that a step further, which tells us very quickly whether or not this can be factored. Do you remember in the quadratic formula? The quadratic formula, we have x, oops, let me erase that, sorry. We have x is equal to negative b plus or minus the square root of b squared minus 4ac, and all that over 2a. Do you remember this term right here, the b squared minus 4ac? There's a term for that. It's called the discriminant. We always used to check to see, for one, whether or not this was positive, because if it was a negative number, then there would be no answer. There would be no solution to the equation. If this discriminant were 0, then we would have just one answer. And if it were positive, finally, we had 2 answers. But there's something else the discriminant can tell us. So here's what we're going to look at in this example right here. My a in this example here is going to be 2. My b is 15, and my c is 18 right here. So let's take a look at my discriminant, b squared minus 4ac. That's going to be 15 squared minus 4 times 2 times 18. 15 squared is going to be 225. minus 4 times 2. 4 times 2 is 8. 8 times 18, well, let's see. 8 times 20 would be 160. And the difference between 18 and 20 is 2. 2 times 8 is 16. So what's 160 minus 16? It's going to be 144. So I have 225 minus 144. 225, let's see, 25, or 5 minus 4, let's start simple, it's just going to be 1. And then I have 22 minus 14, the difference between those two is an 8. So my discriminant, b squared minus 4ac, is 81. When I take the square root of that discriminant, I'm going to get a nice round even 9. So when I take the square root of that, I'm going to get a nice round whole number. The reason for that is 81 is what we call a perfect square. A perfect square is a number that when you take the square root, it's a nice round whole number. It's not a decimal, it's not a fraction. In this case, it's just 9. The number 16 is a perfect square. Why is that? Because the square root of 16 is just 4. 25 is a perfect square because the square root of 25 is just 5. 36 is a perfect square because the square root of 36 is just 6. So here's where we're going with this. The lesson to be learned from this is if you check the discriminant like we did here, and you find that the discriminant is a perfect square, then that tells you right off the bat, yes, it can be factored. If the discriminant is not a perfect square, then it cannot be factored, and you should proceed immediately to using the quadratic formula. And the beauty of this is, if you find that this is not a perfect square, you're already halfway home with finding the quadratic formula answer because you've already plugged in and found the discriminant. That's the biggest piece of the puzzle when using the quadratic formula. So in this case right here, this can be factored. So let's take a look at it right here. I know I need to end up with a 2x squared, so I'm just going to write a 2x and an x. That's the only possible way that can happen. So now I need two factors here. I might split my middle term and say, let's see, 2 times 18 is 36. What are the factors of 36? Well, there's obviously the 2 and the 18 that I just used. There's 3 and 12, and there's 4 and 9. I notice 3 and 12 do indeed combine to give me 15 right there. So I might split this one up as 2x squared plus 3x plus 12x plus 18 is equal to 0 before I were to normally complete this factorization the way I would. So let's take a look at this and kind of see, okay, well, where can we go from here, basically? How can we go about this? I see these have a common factor of x. I'll just write the x. When I factor that out, inside I have 2x plus 3. If I were to distribute that, I would end up with these terms. And my greatest common factor of these is just going to be a 6. Once again, I'll pull that out and get a, oh, excuse me, I need to write a 2x plus 3 in there. So now these have a common factor of 2x plus 3. So I'll write my 2x plus 3. And then I write my remaining terms of x plus 6 equal to 0. And now I've succeeded at factoring this. So once again, just like in the last example, now how would I go about actually solving this? Well, I have this times this is equal to 0. So that means either 2x plus 3 is equal to 0, or x plus 6 is equal to 0. If I were to solve this one, I would subtract off 3 from both sides and get 2x is equal to minus 3. That tells me x is equal to negative 3 halves. Or in this example, I would just subtract off, forgot my minus 0 there, subtract off 6 from both sides and get x is equal to negative 6. So as you see, there is some benefit to still being able to factor this. It was a bit of work to know that we could factor this, but actually it's occasionally it's definitely worth a check because it can lead you to a simple and more direct answer. Let me clear this out right here. Let's go on to one last example right here where factorization is not going to be practical. Let's take a look at this. So I have 10x squared minus 83x plus 24 is equal to 0. So I have this quadratic equation, try to make my 83 a little better there. So I have 10x squared minus 83x plus 24 is equal to 0. Now my problem with this is apparent pretty immediately, that if I were to check the discriminant of this, b squared minus 4ac, that is going to basically say negative 83 squared minus 4 times 10 times 24. Trying to square and calculate all this is just going to be a nightmare, and it is almost certainly not going to be a perfect square. So basically, my suggestion is whenever you see numbers like this, where you're thinking to yourself, squaring this just as a check is going to be totally impractical. These numbers are way too large, they're way too complicated, and they're obviously not numbers like 2 or 6 or 5 or 3 where they're very easy to work with. These numbers here are much more complicated. So in these cases, if we wanted to solve this equation, we really should proceed straight to the quadratic formula. We should just go with something that we know works and not waste our time trying to figure out if it can be factored or not. Another example right here that I'm just going to make up off the top of my head. Let's say that we had something like this, even a more complicated example. We had a 27x squared minus 543x plus 117 is equal to 0. This is a quadratic equation right here. We could attempt to solve something like this, and it probably does have solutions. But that being said, trying to square numbers like this, especially just to check and see if it can be factored, is totally impractical. And with numbers like this, it almost certainly cannot be factored. So it would be a complete waste of time to do anything other than proceed to the quadratic formula in those cases. So let's take a look at one or two more things here real quick. So just basically, how do we know whether or not we should attempt to factor something or not? The things to look for are this. One, are your numbers small and relatively easy to work with? Sometimes you can factor them very directly just by observation. Let's say I had an example like this one. If I have a perfect square, like x squared plus 6x plus 9 is equal to 0, I can factor that one simply from memory. That's x plus 3 and x plus 3 equals 0. I could, if I wanted, write that x plus 3 squared is equal to 0, because anything times itself is that thing squared right there. So this can be factored just by observation. Another example of that would be something like this. If I had, say, x plus 2 and x minus 1, sorry. So what would that look like if I were given a quadratic equation? X times x is x squared, minus x plus 2x is going to be positive x, and positive 2 times negative 1 is going to be a negative 2. So if I were given this one right here, I can see right off the bat how easily that factors right there. So this is one that I can definitely use factoring on. And we saw just a moment ago how even some that are seemingly a little more complicated, like this, like 2x squared plus 15x plus 18, they require a little bit more work, but they can still be factored. Pretty much as long as factorization works, we should probably use it, but there does come a time when these numbers right here become so large and so cumbersome to work with that even if it can be factored, we're kind of defeating the purpose. The whole point of factoring these equations right here is to make them easier to work with. You've got to remember that. That's the whole logic behind attempting to factor something, is it's easy to work with and it makes these easy to solve. So if you ever find that for yourself, that when you're working with these, that this is not making it easier to solve, it's making it just as hard, if not harder than anything, then that's when you should stop using that method and go back to something that you know works. And thankfully we have a tool that, remember, it always works. It doesn't matter what numbers I use in front of these x's. If I have an equation that takes this form, my quadratic formula will always give me the answer. So always be prepared to fall back on that if you ever have any questions on this.